Okay, we start with the observable canonical form. In this we will study introduction, mathematical representation of observable canonical form, and lastly numerical examples. Now about introduction. If you see any state space analysis, what is the final aim? Final aim is to design a controller, and the controller has been designed in the state space using pole placement techniques, and in the pole placement technique there is need to check controllability and observability. So all these issues we will study afterward. So in that case, particularly in case of observability, there is need an observer equations. Therefore we require a model which is of form observable canonical form. Along with this, sometimes required an observer design, because sometimes the states cannot be measured, we have to design an observer. So that in that case also we need a model which is concerned with the observability, or we need an observable canonical form. Therefore today we are going to study the observable canonical form of model. So we start with its mathematical representations. So we will take a same transfer function model which we have taken last time. So y of s equal to u of s equal to bn sn b of n minus 1 sh to n minus 1 plus b1s plus b naught divided by s raised to n a of n minus 1 s raised to n minus 1 plus a of n minus 2 s raised to n minus 2 plus a1s plus a naught. This is the model. So last time when we have determined the state space model, we have written in equation in terms of x. Now here we are concerned with the observability, that means concerned with the output. Therefore we have to write this equation in terms of y. So here, in order to get result clearly, or in order to understand it, I am taking a third order system. So in this case we will take n equals to 3. So when n equals to 3, your model becomes y is by us equal to b3 s cube b2 square plus b1s plus b naught divided by s cube plus a2 square plus a1s plus a naught. So this transfer function s cube, so this is we call as a proper transfer function, and last time we have seen the difference between proper transfer function and strictly proper transfer function. Now as I told, we want observability, so we had to write the equation in terms of y. So here what we write here, okay, we write a differential equation for this. We write d3 y dt cube of y plus this a2 d square by dt square of y plus a1 dy by dt plus a0 into y plus b3 into d cube by dt cube of u plus b2 d square of dt square of u b1 du by dt plus b0 into u. Now we want y, so what we will do, we will write this equation as d cube y of dt cube equal to, so what we will do, all these terms we move this side, this term, these particular terms will move on the right hand side. So what we will get, we will get b3 into d cube of dt cube of u plus, now we will see that this is b d square dt square and this one. So here this will take as common, so we will get as dt square by dt square will get as b2 into u minus a2 into y plus differentiation of b1 into u a1 into y plus b0 into u minus a0 into y. So, we can see it, this equation, this like this, then this and this portion we have taken common. So, we will get b2 into u minus a2 into y plus differentiation of t with this, in bracket we will get b1 into u minus a1 into y plus b0 into u minus a0 into y. So, now we want output equations. So, how to get output equations? So, therefore, what we will do here, we will integrate this equation 3 times, because when we integrate this 3 times we can get y. Therefore, what we will write? I will write as y equals to b3 into u plus, in bracket we write as b2 into u minus a2 into y dt plus double integrations b1 into u minus a1 into y dt plus triple integrations b0 into u minus a0 y into dt. So, we will find that. So, here we have integrate 3 times, that is why we got y, then here d cube. So, we have integrate 3 times, we have got b3 into u, whereas you will find that there is 2 differentiators. So, when we integrate 3 times we will definitely get 1 integrator. Here there is 1 differentiator, when we integrate 3 times, so we will get 2 integrators. So, we will find that there are 2 integrators. Similarly, you will find that there is no integrator is involved, so no differentiator is involved. So, when we are integrating 3 times, so we will get 3 integrators. So, 3 integrators, 2 integrators, 1 and no integrators. Now, we want the state space model. So, prior to this one, what we will do, from this equation we try to develop a block diagram, or we can say Simulink diagram. So, we start with this. So, here y, so I can show here this is y. Now, this y equal to b3 into u, this is b3 into u. So, what I will take? I will take this as b3, this is b3, and now this is u. So, I am writing down this u complete like this, this is u. So, y equals to b3 into u. So, now here after this, now what is this? This is the one integrator is involved. So, here I am showing one integrator here. So, one integrator here, this is integrator. Now, this is integrator I have shown, and now we take one variable, this is x3, and this when integrate, that means x3 dot. So, now this x3 dot equal to b2 into u minus a2 into y. Therefore, I am doing a similar summation block here one b2, and now here this is a2. So, here a2, this a2, this is a minus, and this is y. Now, we will find that for this one we have put one integrator here x3 dot. So, this x3 dot equal to b2 into u, c is a u, and now minus a2 into y. Now, afterward there is another integrator. So, there are another integrator we have to write. So, here we show another integrator, this in 2 integrators. So, first and second, so another integrator we added. So, in this case we take another variable. So, here x2 and this integrator. So, now this double integrator or this one equals to b1 into u minus a1 into y. So, here what we have done, here x2 dot, this is a block, and x2 dot equal to, this is coming b1. So, here is b1, and now here we have to show a1. So, here minus a1 into y. So, we will find that when there are 2 integrators involved, so integrator 2 integrators, b1 into u, so you shown b1 into u, and now here minus a1 into y we have shown like this. Now, we move further. So, now we have 3 integrators. So now 1, 2, 3, so we have to add another integrators. So here I am adding another integrator, and we take another variable x1, and what is this? This is x1 dot, and what is x1 dot? Equals to b0 into u minus a0 into y. So we write as a block like this. This is b0 into u, and here we write down as minus a0 like this. So here we have written the complete Simulink diagram of a plant, and now from this we have to develop a state space model. So in order to develop the state space model, we write the equation of x1 dot, x2 dot and x3 dot. So now x1 dot, so x1 dot equal to b0 into u minus a0 into y. So you will find this. So what is x1 dot? Equal to b0 into u minus a0 into y, and what is y? Y equals to x3 plus b3 into u, that is y here, this plus y equals to x3 plus b3 into u. So we have to replace this equation here. So we will get as b0 u minus a0 into y, x3 plus b3 into u, and if you after solving this equation you will get a0 x3 plus u b0 minus a0 into b3. This is the first equation we have got. Now coming to the second equation. Now what is x2 dot? x2 dot equals to b1 into u plus in bracket minus a1 into y plus x1. So we write as x2 dot equal to x1 plus b1 into u minus a1 into y, y is x3 plus b3 into u. So we will get as x1 plus b1 into u minus a1 x3 minus a1 b3 into u, and after solving we will get as x1 minus a1 into x3 plus u b1 minus a1 into b3. So we got equation of x1 dot as well as x2 dot. Now coming to the equation for x3 dot. So now x3 dot, we will see that x3 dot equals to b2 into u, see here b2 into u plus x2 minus a2 into y, just here this is x3 dot. So we write the equation for x3 dot as x3 dot, that is equals to x2 plus b2 into u minus a2 x3 plus b3 into u, and now we solve it. So what will get x2 minus a2 into x3 plus b2 into u minus a2 b3 into u, and therefore we write as x2 minus a2 into x3 plus u b2 minus a2 into b3. So we have got three equations, we got x1 dot, we got x2 dot and x3 dot. Now we have to write down this in terms of state space model. So we write this as, so we write x1 dot, x2 dot, x3 dot equal to, so x1 dot equal to this into x1, x2, x3 and plus these some elements and with respect to u. So how will write? So x1 dot equals to, here see here x1 dot a0 x3. So elements of x1 and x2 are 0 in this case, only the elements of x3 is there. So we write this equation as 0 0 minus a naught. Now coming to the equation of x2 dot. In x2 dot what we will find that these are terms in for x1, there is term from x3 but there is no term for x2. So term for x2 is 0. So we write this equation as 1 for x1, 0 minus a1. Now coming to the x3 dot. In x3 dot we will find that there is no term for x1, that is x1 is 0, whereas there is term from x2 and x3. So, we write this equation as 0 1 minus a2. Now, coming to the u terms, for u's you will find that for x1 dot this is term b0 into b0 minus a0 into b3. Now, about this x2 dot, this term for u is b1 a1 b3, you get b1 a1 into b3, and particularly the term for x3 dot will get it as what we will get, b2 into a2 into b3. Now, what is the equation for y? So, we will find that what equation of y we written, y equals to x3 plus b3 into u. So, we write output of y as x3 plus b3 into u. So, we write 0 0 0 1, this is x1 x2 x3 plus b3 into u. So, this is the state space model of the system. So, in this state space model, this is A matrix, this is B matrix, this is C matrix, and this is D matrix. Previously, we have seen a controllable canonical form. This is observable canonical form. So, we will find out, is there any relationship exist between controllable canonical form and observable canonical form? Let us see it. So, in order to do it, what we will do? We will take a transpose. So, here we will numerical example we will see later on. First of all, we will see this concept. So, here what we will write? We take the transpose of A observable transpose. So, we will find that. So, it is 0 0 1 a0, 1 0 1 a1, 0 0 1 a2, and even you will find this is the case 0 0 1 a0, 1 0 a1, 0 1 a2. So, if we take the transpose of this, so what we will get? Transpose of it is 0 1 0, 0 0 1, here minus a0 minus a1 minus a2, this is transpose. So, we will find that this A is nothing but the system matrix of a controllable canonical form, that is A controllable. That means what relationship we got? A observable transpose, that is equals to A controllable. Now, you will find the equation for B observable. See here, this is the equation for B observable. So, we will write the equation for B observable equal to B0 minus B3 into A naught, B1 minus here B2 B3 into A2. Now, what we will do? We make transpose of this. So, what happen if you make transpose of this one? So, B observable transpose, what we will get? Let us say this is A1, this is A2 and this is A3, this is A1, this is A2 and A3. So, here in case of observed form, the B matrix we are coming in the original state space model, whereas what happened in case of the controllable canonical form. So, these elements is coming as a C matrix, therefore, this is in nothing but C controllable matrix. Now, about the this matrix, let us say we take this is C matrix. So, we write C transpose observable equal to we get 0 0 1. So, this matrix is nothing but the B matrix of a controllable canonical form, that is here B controllable. This is B controllable, and particularly if you see the observability matrix D observable. So, D observable in this case will get as B3, well B3 it is same as D controllable matrix. So, we will find that there is a relationship between controllable canonical form, observable canonical form, and particularly we find there is an interchange of elements in B and C. More detailed things or whatever I have taught you, you can also see through this one. So, it is given like this here, then this is also like this. So, you can refer this also. Okay, now we start with numerical example. So, when take example ys by rs, that is equal to s square plus 7s plus 2 s cube plus 15 s square plus 62s plus 48. Now, in this case the elements we write here b0 equals to 48, sorry b0 equals to 2, b1 equals to 7, b2 equals to 1. So, this is 1 elements. Then about this is a0. So, a0 equal to 48, a1 equals to 62, then a2 equals to 15. Now, we have to write down this into a observable canonical form. So, what is the form here? X dot. How write x dot? So, you will find. So, x dot equals to 0 0 a0 1 0 a1 0 1 minus a2. So, we write as 0 0 minus 48, 1 0 minus 62, 0 1 minus 15 to x plus. So, you will find that what is the b? The b is this one, this values a b b0 a0 b3 b1 a0 b3 a2 a0 b3. But now you will find that this transfer function is a strictly proper transfer function. So, in this case the value of your b3 is 0, therefore, you will get only b0 b1 and b2. Therefore, write the elements as directly 2 7 1 u, and what is the output y? Output y we write down as, how write down output of y? 0 0 1. So, here we write down as 0 0 1 into x1 x2 x3 plus this is no 0 into u. Now, we take the second example. So, here ys by rs equal to 2s cube plus 7s square plus 12s plus 18 divided by s cube plus 6s square plus 11s plus 9. This is example. Now, again here b0 equals to 18, b1 equals to 12, b2 equals to 7, and here b3 equals to 2, and here a0 equals to 9, a1 equals to 11, a2 equals to 6, this is 6. So, now here we will find that this is a proper transfer function, degree of numerator and denominator are the same. Now, we have to write down in terms of observable canonical form. So, you will find that there is no much change in the A matrix. So, A matrix similarly is like this 0 0 minus 9, 1 0 minus 11, this is a0 a1, so minus 11, and here we will get 0 1 minus 6 plus. Now, here what will happen? Here we have to do the calculation like this b0 into b3 a0, b1 b3 a1, b2 b3 a2. So, here we write down as the elements as 18 minus 9 into 2. So, 18 this minus 9 and b3 is 2. So, 18 minus 9 into second is 12, this 12 minus we take same 9, sorry 9 we can write 11, this is 11 multiplied by same 2, this is 2, and thirdly we have to write as third elements as 7 minus then is 6 multiplied by same 2, and we will get output as 0 0 1 x1 x2 x3, and particularly you will find that you will get two elements, 2 means here the elements b3 will get it. So, when the transfer function involvement of the proper, there is always D element, this is D element, this is C elements. So, D is involved, whereas for strictly transfer function D is zeros. So, this is about the various examples which I have taken for observable canonical form. So, you can also see some references: Ashish Tiwari, Dira Chaudhary, Normal Nice and Kogata. Thank you.